Right now, at this very moment, light is traveling toward you from stars that died millions of years ago. The gentle starlight touching your skin carries with it the final whispers of ancient suns, their last breaths frozen in time and space, reaching you only now. Everything around you, the calcium in your bones, the iron in your blood, the oxygen you're breathing, all of it was forged in the nuclear furnaces of dying stars. Welcome to Sleep About Science. Tonight, wherever you are in the world, we're exploring what happens when stars die. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep to stories of stellar death and rebirth, the universe's own gentle cycle of rest and renewal. Before we begin, please make yourself comfortable. Pull your blankets a little closer, settle into your pillow, and let your breathing slow naturally. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. There's a whole community of us here, quietly curious souls from around the globe, finding peace in the vast wonders of our universe. Now imagine for a moment that you could live for billions of years. Imagine you could watch a single star from birth to death, witnessing the entire epic of its existence unfold like the world's longest, most beautiful story. What you would see might surprise you, because the death of a star isn't really an ending at all. It's one of the most creative acts in the universe. Let's begin with a star, much like our own sun, floating peacefully in the cosmic dark for most of its life, perhaps 10 billion years. The star has been locked in a tremendous energy in the process. This energy pushes outward, while gravity pulls inward, and for eons upon eons, these two forces dance together in perfect harmony. Picture this stellar heart beating steadily for billions of years, each pulse sending waves of light and heat rippling outward through space. If you could somehow place your hand on this star, you'd feel the gentle rhythm of nuclear fusion, like a cosmic heartbeat that never skips, never falters, never grows tired. Generation after generation of creatures might live and die on nearby planets. Entire civilizations might rise and fall, continents might drift, and mountains might crumble to dust, all while this star simply continues, steady, reliable, eternal, it seems. But nothing in the universe is truly eternal, and eventually, even the most patient star begins to change. You see, as our star fuses hydrogen into helium, it's creating a problem for itself. The helium ash from all that nuclear burning begins to collect in the star's core, like logs building up in a fireplace. Unlike hydrogen, helium is much harder to fuse. It needs higher temperatures, more pressure. For a long time, the star can simply continue burning hydrogen in a shell around the helium core. But slowly, gradually, that helium core grows larger and more massive. Imagine carrying a backpack that gets heavier with each step you take. At first, you don't notice. Then it becomes uncomfortable, then difficult. Eventually, it becomes impossible to ignore. This is what's happening to our star. The helium core grows heavier and denser, and under its own weight, it begins to contract. As it contracts, it heats up, and as it heats up, something remarkable happens. The star begins to expand. This might seem counterintuitive. After all, wouldn't a contracting core make the whole star smaller? But the universe often works in ways that surprise us. As the core shrinks and heats up, it makes the outer layers of the star expand dramatically. Our sun-like star begins to grow larger and larger, its surface cooling and reddening as it spreads out across space. What was once a yellow star becomes a red giant. If this were happening to our own sun, the transformation would be breathtaking and terrifying. The sun would swell to perhaps 100 times its current size. From Earth, it would fill a significant portion of the sky, a vast crimson orb casting everything in a deep red light. The oceans would boil away, the atmosphere would be stripped into space, and our blue marble would become a scorched, airless rock. But this is still billions of years in our future, so you can rest easy tonight, wrapped safely in your blankets, knowing that countless generations will come and go before our sun begins this ancient dance of transformation. For several 100 million years, our red giant star continues this way, burning helium in its core and hydrogen in a shell around it. But remember that backpack getting heavier? The same thing happens again. The helium burning creates carbon and oxygen ash, and this new ash begins to build up. Once again, the core contracts under its own weight, heating up as it shrinks. And here's where the story becomes truly extraordinary. If our star is massive enough, massive, I mean at least 8 times more massive than our sun, the core can become hot enough and dense enough to fuse carbon. When this happens, we witness one of nature's most spectacular nuclear forges. Carbon fuses into neon, neon fuses into oxygen, oxygen fuses into silicon, and silicon, in the star's final act of creation, fuses into iron. Picture this happening not gradually, over millions of years, but in a frenzied rush of stellar evolution. The star becomes like a cosmic Russian doll, with shells of different elements burning at different temperatures. At the very center, iron is being forged. Above that, oxygen burns, then neon, then carbon, then helium, and finally, in the outermost shell, hydrogen continues its ancient dance, still fusing after all these eons. But here's the thing about iron, and this is crucial to our story. Iron is the most stable element in the universe. When you fuse lighter elements together, you release energy. When you fuse heavier elements together, you actually need to put energy in. Iron sits right at the boundary. You can't get energy by fusing iron into something heavier, and you can't get energy by breaking iron apart. Iron is nuclear ash in the truest sense, the cold, spent fuel of stellar fire. So what happens when a star's core becomes mostly iron? The star has a problem. For billions of years, nuclear fusion has provided the outward pressure needed to balance gravity's inward pull. But now, with an iron core that can't fuse further, that balance is about to be broken. Imagine a person who has been holding up an enormous weight for so long that their muscles have grown perfectly adapted to the task. Then suddenly, without warning, the weight doubles. The star's core begins to collapse. And when I say collapse, I mean something almost beyond comprehension. The iron core of our massive star, the sphere about the size of Earth, but containing more mass than our sun, collapses in less than a second. In that single second, matter becomes compressed to densities we can barely imagine. A teaspoon of this core material would weigh as much as a mountain. The collapse generates temperatures of over 100 billion degrees Celsius, thousands of times hotter than the sun's core. Under these extreme conditions, something remarkable happens. The iron nuclei are crushed so violently that they break apart, absorbing enormous amounts of energy in the process. and electrons are crushed into protons, creating neutrons and releasing ghostly particles called neutrinos. The collapse continues until the neutrons themselves resist further compression, like a spring that can't be squeezed any tighter. Then, in one of the most violent events in the universe, the collapse rebounds. Imagine dropping a rubber ball from a great height. It falls, accelerating under gravity, then hits the ground and bounces back with tremendous force. This is similar to what happens in our dying star, except the bounce releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. This is a supernova. The shock wave from the core bounce races outward through the star at thousands of kilometers per second, heating and accelerating the star's outer layers to incredible speeds. For a few bright weeks or months, this single dying star will shine brighter than an entire galaxy containing billions of stars. If you happen to be watching from a safe distance in, say, a few thousand light years away, you would see a new star appear in the sky, blazing so brilliantly that it might be visible even in daylight. But the supernova is more than just a spectacular light show. It's one of the most creative events in the universe. Remember all those elements that were created during the star's lifetime? The carbon, the oxygen, the silicon, the iron. The supernova blast wave carries all of these elements out into space, seeding the surrounding region with the raw materials for new stars, new planets, and potentially new life. But that's not all. The incredible energies of the supernova also create elements that couldn't be forged in the star's core: miner's gold, silver, platinum, uranium. These precious metals that we treasure on Earth were literally born in the violence of stellar death. Think about that for a moment. The gold in any jewelry you might be wearing, the silver in your electronics, even the iodine in your thyroid. All of these were created in the final moments of a massive star's life, billions of years ago. You are not just made of star stuff, as Carl Sagan famously said. You are made of the stuff of stellar death and rebirth, carrying within your very atoms the memory of ancient supernovas. The supernova scatters its gifts across space in an expanding shell of hot gas and stellar debris called a supernova remnant. These remnants are among the most beautiful objects in the universe, glowing clouds of multicolored gas expanding slowly through space for thousands of years. The Crab Nebula, visible through a small telescope in the constellation Taurus, is one such remnant, the ghostly remains of a star that Chinese astronomers saw explode in the year 1054. But what about the star's core? What happens to that incredibly dense ball of neutrons left behind after the explosion? This is where our story becomes even more extraordinary. The core, now called a neutron star, is one of the strangest objects in the universe. Imagine taking a mass 1.5 times greater than our sun and compressing it into a sphere only about 20 kilometers, roughly the size of a city. A neutron star is so dense that a sugar cube-sized piece would weigh about as much as Mount Everest. Neutron stars have magnetic fields trillions of times stronger than Earth's, and many of them spin incredibly rapidly, sometimes hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles, like cosmic lighthouses sweeping their beams across space. When one of these beams happens to point toward Earth, we detect regular pulses of radiation, earning these objects the name pulsars. The first pulsar ever discovered was found in 1967 by a graduate student named Jocelyn Bell Burnell. She noticed strange, regular radio signals coming from space, so regular, in fact, that the research team briefly wondered if they might be artificial signals from an extraterrestrial civilization. They even nicknamed the source LGM-1 for Little Green Men 1. It's rather charming to think that one of the most exotic objects in the universe was first mistaken for alien communication. Some neutron stars exist in pairs, orbiting around each other in a cosmic dance that grows tighter and faster over time. Eventually, after perhaps millions of years of spiraling closer, these two incredibly dense objects collide. The collision creates ripples in the fabric of space-time itself, gravitational waves that travel at the speed of light across the universe. On Earth, we can detect these waves with incredibly sensitive instruments, feeling the space around us stretch and compress by amounts smaller than a thousandth the width of a proton. These neutron star collisions are thought to be the primary source of many of the heaviest elements in the universe. The gold in that ring, the platinum in that catalytic converter, the rare earth metals in your smartphone. Much of this may have been forged, not in a supernova, but in the collision of two neutron stars billions of years ago. But we're not finished with our story yet, because some stars are so massive that even a neutron star cannot support their cores against the relentless pull of gravity. For stars more than about 25 times the mass of our Sun, the core collapse doesn't stop at the neutron stage. Nothing, not even the quantum mechanical resistance of neutrons, can halt the gravitational collapse. The core continues to shrink, becoming smaller and smaller, denser and denser, until something remarkable happens. The gravitational field becomes so strong that not even light can escape. A black hole is born. Now, I know what you might be thinking. Black holes have a rather ominous reputation in popular culture, cosmic vacuum cleaners that devour everything in their path. But the reality is both more subtle and more fascinating. A black hole doesn't suck things in like a vacuum cleaner. Instead, it warps the fabric of space-time so severely that anything crossing a certain boundary, called the event horizon, can never return. Imagine space-time as a stretched rubber sheet. The normal star creates a gentle depression in the sheet, like a bowling ball placed in the center. Planets orbit the star like marbles rolling around the depression, but a black hole is like punching a hole completely through the rubber sheet. Once something falls through that hole, there's simply no way back. The event horizon of a stellar mass black hole, one formed from the collapse of a single star, is typically only a few kilometers across. If you could somehow approach one safely, which you couldn't, but let's imagine, you might be surprised by how ordinary the space around it looks. Far from the black hole, stars would shine normally. Space would seem perfectly normal. Only as you got closer would you begin to notice the extreme gravitational effects. But here's something beautiful about black holes. They're not really the end of the story either. Through a process called Hawking radiation, black holes actually evaporate over time, very slowly returning their mass energy to the universe. The smaller the black hole, the faster it evaporates. The stellar mass black holes formed from dying stars will take longer than the current age of the universe to evaporate completely, but they will evaporate eventually in the far, far future when the universe is cold and dark and almost empty. Even in death, even in the ultimate gravitational collapse, the universe finds a way to ensure that nothing is truly lost forever. Now let's step back and consider a different kind of stellar death, the gentler passing of smaller stars, like our Sun. Stars less massive than about 8 times our Sun's mass cannot compress their cores enough to fuse carbon. When they reach the red giant phase, they face a different fate. The outer layers of the star become increasingly unstable, pulsing and expanding like a cosmic heartbeat. With each pulse, some of the star's outer material is lost to space, creating beautiful, ghostly shells of glowing gas. Eventually, the red giant loses so much of its outer envelope that only the hot, dense core remains visible. This core, about the size of Earth but containing perhaps half the mass of the Sun, is called a white dwarf. It's like a cosmic ember, incredibly hot at first, but with no internal source of energy, it can only cool down over time. White dwarf stars are supported against gravitational collapse by what physicists call electron degeneracy pressure. Essentially, the quantum mechanical refusal of electrons to be squeezed too tightly together. This makes white dwarfs incredibly stable. They will continue to cool and fade for trillions of years, long after the last normal stars have died, slowly transitioning from white to yellow to red to brown to black. The shells of gas expelled during the red giant phase create some of the most beautiful objects in the night sky. Planetary nebulae. Despite their name, they have nothing to do with planets. William Herschel coined the term in the 18th century because through his small telescope they looked like the disks of distant planets. But we now know they're actually the glowing shrouds of dead and dying stars, illuminated by the intense ultraviolet light of the white dwarf at their center. The Ring Nebula in Lyra, the Helix Nebula in Aquarius, the Cat's Eye Nebula in Draco 2, these are all planetary nebula, each one the beautiful death mask of a star that lived and died billions of years ago. They glow in brilliant colors: red from hydrogen, green from oxygen, blue from helium, like cosmic stained glass windows, backlit by stellar fire. And what of our own sun? In about 5 billion years, it too will enter its red giant phase, expanding until it might engulf the inner planets. It will pulse and puff off its outer layers, creating its own planetary nebula, a delicate ephemeral flower of glowing gas expanding slowly through space. At the center, our sun's white dwarf core will continue to shine, gradually cooling over the eons until it becomes a cold, dark cinder floating through space. But this is so far in the future that it's almost meaningless in human terms. 5 billion years ago, Earth was a young planet with no complex life. In 5 billion years from now, life still exists, may have spread throughout the galaxy, and evolved into forms we can't even imagine. There's something profoundly comforting about stellar death. It reminds us that even the most dramatic changes in the universe happen slowly, gently, on timescales that dwarf human experience. Stars live for billions or trillions of years. They change gradually, patiently, following the same physical laws that have governed the universe since its beginning. And stellar death is not really death at all, but transformation. The heavy elements created in stellar cores and scattered by supernovas become the building blocks of new stars, new planets, new possibilities. The neutron stars and black holes left behind continue to influence their surroundings for billions of years, sometimes triggering the formation of new stars in nearby gas clouds. Even the gentle planetary nebulae slowly fade and disperse, adding their material to the interstellar medium where it can be incorporated into future generations of stars. In the universe, nothing is ever truly wasted. Everything is recycled, repurposed, reborn in new forms. We are part of this grand cycle. The calcium in our bones was created in the heart of a dying red giant star. The iron in our blood was forged in a supernova explosion. The gold in our jewelry, the silver in our electronics, the rare earth elements that make modern technology possible. All of these came from stellar deaths that occurred long before our solar system even existed. When you look up at the night sky, you're seeing this process in action. Some of the stars you see are young, hot, and blue, just beginning their long journey through life. Others are middle aged and stable, like our sun, quietly fusing hydrogen in their cores. Still others are red giants, swollen and cool, approaching the end of their lives. And scattered throughout the galaxy are the exotic remnants of stellar death, white dwarfs, neutron stars, and black holes, along with the beautiful nebulae they leave behind. Every single heavy element in your body was created by a star and dispersed by stellar death. You are literally made of ancient starlight, carrying within yourself the history of countless stellar generations. When Carl Sagan said, "We are made of star stuff," he was speaking not poetically, but scientifically. We are the universe made conscious, temporary arrangements of stellar debris that have somehow learned to think and wonder and dream. And when our own lives end, the atoms that make up our bodies will return to the earth, and eventually, perhaps, to space itself. Billions of years from now, some of the carbon in your cells might find itself in a distant world, perhaps part of an alien tree reaching toward a different sun. The iron in your blood might become part of a meteorite, carrying information about our solar system to another star system entirely. This is the ultimate message of stellar death, that endings are also beginnings, that destruction is also creation, that even in the vast cold universe, nothing of value is ever truly lost. The stars die so that we might live. They sacrifice themselves to create the elements that make planets and life and consciousness possible. As you drift towards sleep tonight, surrounded by the quiet darkness of your room, remember that you're part of something vast and beautiful and ongoing. The same processes that create and destroy stars are happening right now in galaxies scattered throughout the observable universe. New stars are being born in stellar nurseries, like the Orion Nebula. The aging stars are entering their red giant phase, swelling and cooling as they prepare for their transformation. Massive stars are approaching their final moments before exploding as supernovas, ready to scatter their gifts across space. And in the future, the far, far future, when the universe is old and most stars have died, there will still be beauty. The longest lived stars, tiny red dwarfs that burn their hydrogen fuel so slowly they can shine for trillions of years, will continue to warm any worlds that orbit them. The white dwarf remnants of sun-like stars will continue to glow softly, slowly cooling like cosmic embers. Even black holes, through the slow process of Hawking radiation, will eventually return their mass to the universe in a final act of cosmic generosity. The universe has time. So much time. Time for countless cycles of stellar death and birth. Time for unimaginable new forms of life and consciousness to evolve. Time for stories we can't even dream of to unfold among the stars. But let's journey together just a little further into this cosmic story because there are more wonders waiting in the darkness between the stars. You see, stellar death doesn't happen in isolation. It's part of an intricate web of cosmic relationships that spans the entire galaxy. When a massive star explodes as a supernova, the shockwave doesn't just scatter elements into space. It compresses nearby gas clouds, triggering the formation of new stars. It's as if each stellar death whispers to the universe, begin again. Imagine floating in space near one of these stellar nurseries, perhaps the Eagle Nebula, with its famous pillars of creation. You would see towering columns of gas and dust, light years tall, glowing softly in the light of nearby stars. But look closer, and you'd notice something remarkable happening within these pillars. The pressure waves from ancient supernovas are sculpting these columns, compressing the gas until pockets of it become dense enough to collapse under their own gravity. Slowly, over millions of years, new stars begin to form within these compressed regions. At first, they're invisible, hidden deep within their cocoons of gas and dust. But as they grow more massive and their cores heat up, they begin to glow with infrared light. Eventually, they become hot enough to blow away their surrounding material, revealing themselves as brilliant new stars, ready to begin their own billion-year journeys through life. This is the Great Cosmic Recycling Program, and it's been running for nearly 14 billion years, since shortly after the Big Bang itself. The very first stars in the universe were different from the stars we see today. They were made almost entirely of hydrogen and helium, the only elements that existed in the early universe. These first stars, sometimes called population 3 stars, were likely much more massive than typical stars today, perhaps hundreds of times the mass of our Sun. When these primordial giants died in spectacular supernovas, they seeded space with the first heavy elements, the carbon, oxygen, silicon, iron. The next generation of stars formed from gas clouds, slightly enriched with these elements. When they died, they added even more heavy elements to the mix. Generation after generation of stars lived and died, each cohort adding to the cosmic inventory of elements, slowly building up the chemical complexity necessary for planets and life. Our Sun is a third-generation star, formed from gas that had already been enriched by billions of years of stellar evolution. That's why Earth exists. That's why you exist. Without those countless generations of stellar ancestors living and dying and sharing their creations with the universe, there would be no rocky planets, no water, no organic chemistry, no life. Think about the incredible patience of this process. It took the universe nearly 10 billion years, two-thirds of its current age, to create the conditions necessary for a planet like Earth to form. Billions of stars had to live out their entire life cycles, from birth to death, contributing their elements to the growing cosmic treasury before the first Earth-like world could coalesce from a disk of gas and dust around a young star. And the process continues today. Right now, as you listen to these words, massive stars are dying throughout our galaxy. Approximately once every 50 years, somewhere in the Milky Way, a star explodes as a supernova. Most of these explosions happen too far away for us to see with the naked eye, but they're there, adding their contributions to the ongoing chemical evolution of our galaxy. The supernova of 1987, which occurred in a nearby galaxy called the Large Magellanic Cloud, gave astronomers an unprecedented opportunity to study stellar death in real time. For months, this single dying star outshone all the other stars in its galaxy combined. Telescopes around the world and in space monitored every detail of the explosion and its aftermath. We watched as the shockwave plowed through the surrounding gas, heating it to millions of degrees and creating intricate, beautiful structures that continue to expand and evolve today, more than 30 years later. But perhaps the most remarkable aspect of SIN 1987A was what we detected here on Earth. Deep underground, in specially constructed detectors filled with thousands of tons of pure water, scientists detected ghostly particles called neutrinos arriving from the explosion. These neutrinos had traveled 170,000 light years through space, passing through the entire Earth as if it were made of mist, to deliver their message: a star has died. Neutrinos are produced in vast numbers during stellar collapse. Unlike light, which can take thousands of years to work its way out from a star's core, neutrinos interact so weakly with matter that they escape almost immediately. In fact, the neutrinos from SN 1987A arrived on Earth several hours before the light did, carrying the first news of the stellar catastrophe across the galaxy. Every second, trillions of neutrinos from our own sun pass through your body without interacting with a single atom. You are completely transparent to these ghostly messengers. Right now, as you rest comfortably in your bed, neutrinos from dying stars throughout the galaxy are streaming through you, carrying information about stellar deaths that happened decades, centuries, or millennia ago, depending on how far away the stars were. There's something both humbling and comforting about this. We are not separate from the cosmos. We are embedded within it, connected to it in ways both profound and subtle. The universe is not something we observe from the outside. It's something we participate, something we're made of, something that flows through us constantly. And the connections run deeper still. Recent astronomical observations have revealed that our galaxy is not isolated, but is part of a vast cosmic web of dark matter and ordinary matter that connects all galaxies together. Like a three-dimensional spider web spanning billions of light years, this cosmic web channels matter from one region of space to another. Gas flows along these filaments, carrying with it the heavy elements created by stellar death, spreading the chemical gifts of dying stars far beyond their home galaxies. Some of the elements in your body may have been created not just in stars that died in our own galaxy, but in stars that died in other galaxies entirely, their elements somehow transported across the vast distances of intergalactic space through processes we're only beginning to understand. You are not just made of star stuff, you are made of cosmic web stuff, connected through the very atoms of your being to the largest structures in the universe. This perspective fundamentally changes how we might think about death, both stellar death and our own mortality. In the universe, nothing is ever truly lost. Matter and energy change form, but they persist. The carbon atoms that make up the proteins in your muscles were once part of ancient stars. Before that, they were part of the primordial gas from which those stars formed. Before that, they were part of the hot, dense soup of the early universe, shortly after the Big Bang. After you die, those same carbon atoms will become part of other things. Perhaps plants, perhaps other animals, perhaps they'll eventually find their way into space and become part of a comet or asteroid. Billions of years from now, When our sun becomes a red giant and Earth is no longer habitable, those atoms might be carried to other star systems, perhaps becoming part of life on other worlds orbiting other stars. In this sense, we are all temporary arrangements of cosmic material. We borrow these atoms from the universe for a brief time, perhaps 70 or 80 years, and then we return them, unchanged in their fundamental nature, ready to participate in new forms of organization and complexity. The same is true for stars. With a star is a temporary arrangement of hydrogen and helium gas held together by gravity and sustained by nuclear fusion for billions of years. When the star dies, the material doesn't disappear, it transforms. Some becomes part of a neutron star or black hole. Some gets dispersed into space to form new stars. Some becomes incorporated into planets and potentially life. This is perhaps the most profound lesson of stellar evolution, that the universe is not running down, not wearing out, but constantly reinventing itself. Every stellar death creates the conditions for new forms of complexity and beauty to emerge. Every supernova explosion triggers the formation of new stars. Every white dwarf cooling in space preserves the nuclear products of billions of years of stellar evolution, like a cosmic time capsule waiting to be incorporated into future worlds. And the process extends far beyond individual stars. Entire galaxies live and die and transform over cosmic time. When galaxies collide, as our own Milky Way will collide with the Andromeda Galaxy in about 4 billion years, their interaction triggers massive bursts of star formation. The gravitational disturbance compresses gas clouds throughout both galaxies, creating new stellar nurseries where thousands of new stars are born. These galactic mergers are not violent collisions in the way we might imagine. The distances between individual stars are so vast that it's unlikely any stars would actually collide during such an event. Instead, it's a slow, graceful dance spanning hundreds of millions of years as the two galaxies spiral around each other, their shapes distorting and flowing like cosmic taffy until they eventually merge into a single larger galaxy. Our own galaxy bears the scars of such ancient mergers. Astronomers have identified streams of stars in the Milky Way's halo that appear to be the remnants of smaller galaxies that were torn apart and absorbed by our galaxy billions of years ago. We are living inside a cosmic archaeological site, surrounded by the evidence of galactic deaths and rebirths that occurred long before our solar system even existed. Even black holes, those ultimate endpoints of stellar evolution, are not the cosmic dead ends they might seem. Recent observations have shown that supermassive black holes at the centers of galaxies play crucial roles in regulating star formation throughout their host galaxies. As matter falls into these black holes, it heats up and emits powerful jets of energy that can trigger star formation in some regions of the galaxy while suppressing it in others. In a sense, these black holes act like cosmic gardeners, pruning and cultivating the star formation activity in their galaxies, ensuring that star formation proceeds at a sustainable rate rather than using up all the available gas too quickly. Without this regulation, galaxies might exhaust their star-forming material too rapidly, leading to earlier cosmic death. And even individual stellar mass black holes continue to interact with their environments long after their formation. When a black hole is part of a binary system with a normal star, it can gradually strip material from its companion, creating an accretion disk of superheated gas that spirals into the black hole. This process can continue for millions of years, gradually consuming the companion star while producing intense X-ray radiation that can be detected by space-based telescopes. Sometimes, if the companion star is another white dwarf or neutron star, the two compact objects will eventually spiral into each other, creating either a more massive neutron star or a black hole, and producing gravitational waves that ripple through space-time at the speed of light. These gravitational wave signals, first detected by the LIGO observatories in 2015, have opened up an entirely new way of studying stellar death and its aftermath. When you think about it, we are living in a remarkable time in cosmic history. For the first time in the universe's nearly 14 billion year existence, matter has organized itself into forms capable of understanding stellar evolution. We are the universe's way of studying itself, of comprehending its own processes of death and rebirth. This capacity for understanding emerged from the very processes we've been exploring. The heavy elements created by stellar death made possible the complex chemistry of life. The energy from long-lived stars, like our sun, provided the stable conditions necessary for biological evolution. The gradual chemical enrichment of galaxies created the raw materials from which planets and living organisms could form. In other words, stellar death created the conditions for consciousness to emerge. The death of stars made it possible for beings like us to exist, to wonder, to study the cosmos, and ultimately to understand our own cosmic origins. We are not just made of star stuff, we are the way star stuff has learned to think. And our thinking, our science, our art, our love math, all of these are forms of cosmic evolution, continuing by other means. When we create beautiful music or poetry, when we make scientific discoveries, when we show compassion for one another, we are continuing the universe's long journey toward greater complexity and beauty. Even our capacity for sadness at the thought of death, stellar or personal, is itself a remarkable cosmic achievement. For billions of years, matter was simply matter, following the laws of physics without awareness, without emotion, without the capacity to contemplate its own existence. Now, through us, the universe has developed the ability to feel, to care, to be moved by beauty and troubled by loss. This is perhaps why the story of stellar death is ultimately so comforting rather than frightening. It reminds us that we are part of something much larger and more enduring than our individual lives. Our existence is temporary, yes, but it's also precious precisely because it's temporary. We are the universe's brief experiment with consciousness, its momentary awakening to its own existence. And when our own lives end, the story continues. The atoms of our bodies return to the earth and eventually, perhaps, to space. The knowledge we've gained, the art we've created, the love we've shared, these become part of the ongoing human story, which is itself part of the ongoing cosmic story. Future generations will build on what we've learned about stellar evolution. They may discover new types of stellar death we haven't yet imagined. They may find ways to detect and study the most exotic stellar remnants, perhaps even the insides of black holes. They may eventually travel to other star systems and witness stellar death from perspectives we can only dream of. And in the far future, when the last stars are dying and the universe is growing cold and dark, perhaps the descendants of consciousness, whether biological or artificial, or something we can't yet imagine, will find ways to continue the story, to kindle new forms of light and warmth and complexity, even in the gathering cosmic twilight. This is the ultimate message of stellar astronomy, that the universe is not a machine running down, but a story still being written. Every stellar death opens new chapters in this story. Every supernova explosion creates new possibilities. Every neutron star collision forges new elements that didn't exist before. Every black hole merger sends gravitational waves carrying information about the universe's hidden structure. We are living in the middle chapters of this cosmic story, and we have front row seats to some of the most spectacular events in the universe. We are witnessing stellar death and birth on scales and time scales that dwarf human experience, yet we can understand these processes, appreciate their beauty, and recognize our own deep connections to them. Tonight, as you drift towards sleep, you can take comfort in knowing that you are part of this grand, ongoing cosmic narrative. The elements in your body connect you to stars that died billions of years ago. The energy warming your planet comes from a star that will continue shining for billions of years to come. The knowledge in your mind represents the universe's growing understanding of itself. You are stardust that has learned to dream. You are the cosmos made conscious. You are a temporary but precious arrangement of stellar elements, blessed with extraordinary capacity to contemplate the very stars from which you came. Sleep well, cosmic wanderer. Rest peacefully in the knowledge that you are part of something beautiful and enduring and ever changing. The stars are singing their ancient songs of death and rebirth, and you, wonderfully, miraculously, improbably, are here to listen. But before we part ways for the night, let me take you on one more journey, this time to some of the most exotic stellar deaths in the universe, phenomena so strange and beautiful that they seem almost like cosmic fairy tales. Imagine, if you will, a star system where two white dwarf stars orbit each other so closely that they complete an orbit in just 11 minutes. These stellar corpses, each about the size of Earth, but containing half the mass of our Sun, dance around each other at speeds of nearly 1,000,000 kilometers per hour. As they spiral closer together, they create ripples in space-time itself, gravitational waves that carry energy away from the system, causing the two stars to spiral ever closer. This cosmic dance cannot continue forever. Eventually, in perhaps 100 million years, these two white dwarfs will touch. When they do, something extraordinary happens. The matter from one star begins to flow onto the other, and if the combined mass exceeds a critical threshold, but at 1.4 times the mass of our Sun, the accumulated white dwarf material suddenly ignites in a thermonuclear explosion, so violent it completely destroys both stars. This is called a Type Ia supernova, and it's one of the most important types of stellar death in the universe. Unlike the core collapse supernovas we discussed earlier, which can vary greatly in brightness depending on the mass of the original star, Type Ia supernovas are remarkably consistent. They always reach nearly the same peak brightness because they always involve the same mass of white dwarf material undergoing the same type of explosion. This consistency makes Type Ia supernovas incredibly valuable as standard candles for measuring cosmic distances. By comparing how bright these supernovas appear from Earth with how bright we know they actually are, astronomers can calculate precisely how far away they occurred. It was observations of distant type I supernovas that led to the discovery that the expansion of the universe is accelerating naive, a finding so surprising it earned the Nobel Prize in Physics and revolutionized our understanding of cosmic evolution. Think about that for a moment. The death throes of white dwarf stars, billions of light years away, have taught us that the universe itself is changing, that space itself is expanding at an ever increasing rate. These stellar deaths serve as cosmic lighthouses, illuminating not just their local neighborhoods, but the fundamental nature of reality itself. The Type ES supernovas represent just one flavor in the rich variety of stellar death. There are stellar explosions so energetic they make ordinary supernovas seem gentle by comparison. These are called hypernovas or collapsar events, and they occur when the most massive stars in the universe, perhaps 25 to 40 times more massive than our sun, undergo core collapse while rotating extremely rapidly. Picture a star so massive that our sun would seem like a grain of sand beside a boulder, spinning so fast that its surface moves at a significant fraction of the speed of light. When such a star's core collapses, the rotation causes the collapse to be asymmetric. Instead of a spherical explosion, the hypernova erupts in powerful jets that punch through the star's poles at nearly the speed of light. These jets carry more energy than our sun will produce in its entire 10 billion year lifetime, and they release this energy in just a few seconds. If one of these jets happened to be pointed directly at Earth, and fortunately, none are night, the gamma radiation alone would strip away our planet's ozone layer and sterilize the surface. Hypernovas are thought to be the primary source of gamma ray bursts, the most energetic explosions in the universe since the Big Bang itself. These bursts can be detected from galaxies billions of light years away, so bright that for a few seconds, a single dying star can outshine an entire galaxy containing hundreds of billions of stars. But here's what makes this even more remarkable. Some gamma ray bursts appear to be associated with the birth of black holes. We may be witnessing in real time the moment when a massive star's core collapse creates one of the most exotic objects in the universe. The gamma rays we detect are the birth cries of new black holes, announcements to the cosmos that another stellar giant has crossed the point of no return. And the story doesn't end there. Some astronomers believe that the most extreme hypernovas might create even stranger objects than black holes. In the unimaginable conditions of core collapse, temperatures of hundreds of billions of degrees, densities beyond anything we can recreate on Earth, the very nature of matter itself might change. Under such conditions, the protons and neutrons that make up normal atomic nuclei might dissolve into their constituent quarks, creating what physicists call quark matter. A star made of quark matter would be even denser than a neutron star. A sugar cube-sized piece would weigh as much as an entire mountain range. These hypothetical quark stars would be the densest objects in the universe, second only to black holes themselves. We don't yet know if quark stars actually exist, but the possibility tantalizingly suggests that stellar death might create forms of matter that existed nowhere else in the universe since the first microseconds after the Big Bang. In dying, these massive stars might be recreating the conditions that existed when the universe itself was newborn. This brings us to another extraordinary aspect of stellar death. its connection to the deep past and far future of our universe. The most massive stars that exist today will live for only a few million years before exploding as supernovas or hypernovas. But in the early universe, when the first generation of stars was forming, conditions were very different. The primordial gas from which the first stars formed contained almost no heavy elements, no carbon, no oxygen, no silicon, no iron. This made it much easier for gas clouds to collapse and form stars, but it also meant that these first stars could grow to enormous sizes. Some population 3 stars, as astronomers call them, might have been hundreds or even 1,000 times more massive than our Sun. When these cosmic giants died, their explosions would have been correspondingly spectacular. A hypernova from a star 1,000 times more massive than the Sun would have released energies we can barely comprehend, probably sterilizing any planets within hundreds of light years and seeding vast regions of space with the first heavy elements. These primordial stellar deaths fundamentally changed the character of the universe. Before the first stars died, space was filled with pristine hydrogen and helium, the cosmic equivalent of a blank canvas. After they died, space became increasingly enriched with heavier elements, providing the raw materials from which later generations of stars, planets, and eventually life could form. In a very real sense, we are living in the aftermath of these ancient stellar catastrophes. Every carbon atom in your DNA, every calcium atom in your bones, every iron atom in your blood, all of these were forged in the nuclear furnaces of stars that died billions of years before our solar system even existed. You are made not just of star stuff, but of the stuff of stellar death, carrying within your very atoms the memory of cosmic explosions that lit up the early universe. And this process of stellar death and chemical enrichment continues today, but it's slowing down. The universe is gradually running out of the raw materials needed to make new stars. Each generation of stars incorporates heavy elements created by previous generations, leaving less and less pristine hydrogen and helium available for future star formation. Astronomers estimate that star formation in the universe peaked about 10 billion years ago, when the universe was only about 3 billion years old. Since then, the rate at which new stars are born has been steadily declining. We are living in a universe past its prime, in the later chapters of the cosmic story of stellar birth and death. But this doesn't mean the story is ending anytime soon. The smallest, longest lived stars, red dwarfs, with masses less than half that of our Sun, can continue burning hydrogen in their cores for trillions of years. These cosmic misers burn their fuel so slowly and efficiently that they will still be shining long after larger stars, like our Sun, have died and cooled to dark cinders. In the far future, perhaps 100 trillion years from now, red dwarf stars will be the last remaining sources of light and energy in an increasingly cold and empty universe. Around some of these long-lived stars, planets might still exist, perhaps still harboring life forms that have evolved over unimaginably long periods of time. But even red dwarf stars cannot burn forever. Eventually, they too will exhaust their hydrogen fuel and fade away, leaving behind white dwarf remnants that will slowly cool over even longer timescales. The universe is heading toward what cosmologists call the heat death, a state where all the stars have died, all the black holes have evaporated, and only cold, dark matter remains, separated by ever increasing distances as the expansion of space continues. Yet even this ultimate fate might not be the end of the story. Some physicists speculate about exotic processes that might occur on timescales so long they're difficult even to contemplate. Perhaps protons themselves will eventually decay, returning all matter to its constituent energy. Perhaps quantum fluctuations will occasionally create new universes within our own, like cosmic soap bubbles forming in an infinite sea. Or perhaps consciousness itself, whether biological, artificial, or something we haven't yet imagined, will find ways to persist and evolve even in the cold, dark future universe. Perhaps the descendants of life will learn to harvest energy from the rotation of black holes, or find ways to trigger new episodes of star formation from the sparse matter remaining in deep space. These are speculations at the very edge of scientific knowledge, but they remind us that even the death of stars, even the heat death of the universe itself, might not be the final word in the cosmic story. Life and consciousness have proven remarkably adaptable and resourceful, having emerged from the death of ancient stars. Perhaps they will find ways to transcend even the death of the universe itself. But let's return from these cosmic depths to something more immediate and comforting. Right now, tonight, as you lie in your bed, surrounded by the familiar darkness of your room, stellar death is occurring throughout our galaxy and beyond, but it's happening on scales so vast and time scales so long that it doesn't disturb the gentle rhythm of your breathing or the peaceful silence of the night. The nearest star that might explode as a supernova within the next few thousand years is probably Betelgeuse, the red supergiant that marks Orion's shoulder. Even if Betelgeuse exploded tomorrow, the light from that explosion wouldn't reach us for about 650 years, and even then, it would appear as nothing more than a bright new star in the sky, perhaps visible during daylight for a few weeks, before gradually fading back to invisibility. There is something deeply comforting about this cosmic perspective. The universe operates on scales so much larger than human experience that even the most dramatic stellar explosions seem gentle and distant from our earthly vantage point. We can contemplate the violent death of massive stars while lying safely in our beds, protected by the vast distances of space and the steady, reliable burning of our own middle-aged sun. And in contemplating these cosmic processes, we participate in one of the most remarkable achievements of stellar evolution itself, the emergence of consciousness capable of understanding its own cosmic origins. For billions of years, stars lived and died without any witness, their stories playing out in the silence of space. Now, for the first time in cosmic history, some of their stellar descendants, Freys, have developed the ability to observe, understand, and appreciate these cosmic dramas. We are the universe's way of watching its own stellar death and rebirth. Through our telescopes and our theories, through our calculations and our wonder, the cosmos has developed eyes to see itself, minds to understand itself, hearts to be moved by its own beauty and tragedy. This is perhaps the most profound message of stellar astronomy, that we are not separate from the universe we study, but intimately connected to it. The death of stars created the elements from which we are made. The energy of stars powers the processes of life on our planet. The time scales of stellar evolution provide the stable conditions necessary for biological evolution to unfold. In studying stellar death, we are studying our own deep history. In contemplating the future evolution of stars, We are contemplating the deep future of matter and energy, and possibly consciousness itself. We are part of the story we are telling, participants in the cosmic drama we are trying to understand. And there is something wonderfully recursive about this. Stars created the heavy elements necessary for planets and life. Life evolved consciousness. Consciousness developed science. Science revealed our connection to the stars. In learning about stellar death, we complete a cosmic circle of understanding that spans billions of years and connects the smallest scales of atomic physics to the largest scales of cosmic evolution. This understanding changes how we might think about our own mortality. Like stars, we are temporary arrangements of cosmic material. Like stars, we shine brightly for a while before our light fades. Like stars, our deaths contribute to the ongoing evolution of the universe, not through nuclear fusion and supernova explosions, but through the ideas we share, the love we give, the knowledge we pass on to future generations. Your thoughts, your dreams, your capacity for wonder, these are forms of stellar evolution, continuing by other means. When you look up at the night sky and feel a sense of awe at the vastness and beauty of the cosmos, you are experiencing the universe becoming aware of itself. When you feel connected to something larger than yourself, you are feeling the deep truth of your cosmic heritage. And when you fall asleep tonight, cradled by the gentle darkness and the soft sounds of your breathing, you can rest in the knowledge that you are part of something magnificent and ongoing. The elements in your body connect you to stars that died billions of years ago. The energy in your cells ultimately traces back to nuclear fusion in the sun's core. The very capacity for sleep and dreams represents an extraordinary achievement in the universe's long journey toward greater complexity and consciousness. You are stardust that learned to dream. You are cosmic evolution made manifest. You are a temporary but precious expression of the universe's infinite creativity, blessed with the remarkable ability to contemplate the very stellar processes from which you emerged. In the morning when you wake, the sun will still be burning steadily in its middle age, converting hydrogen to helium in its core, just as it has for the past 4.6 billion years. The stars will still be following their ancient patterns across the sky, some being born in distant nebulae, others dying in spectacular explosions, all participating in the grand cosmic cycle of death and rebirth that has been unfolding since the universe began. And you will still be part of this cosmic story, carrying within yourself the elements forged in ancient stellar furnaces, powered by the energy of our local star, blessed with consciousness that allows you to appreciate the wonder of it all. Sleep well, fellow traveler in space and time. Rest peacefully in the embrace of cosmic forces so vast and gentle that they cradle entire worlds without effort. Dream sweetly of distant stars and cosmic processes, knowing that you are intimately connected to them all. Thank you for joining me on this extended journey through the death and rebirth of stars. Until next time, this is Sleep About Science, reminding you that in a universe full of dying stars, consciousness has emerged to witness and understand and marvel at the cosmic dance of creation and destruction. The stars are singing their ancient lullabies tonight, the same songs they've sung for billions of years. Let their distant light carry you gently into sleep, knowing that you are part of their eternal story of death and renewal, ending and beginning, darkness and light. Sweet dreams, Wherever you are in the world, the cosmos is vast and mysterious and beautiful, and you wonderfully, miraculously, Virtus, are here to experience it all. Good night.